This is a video on distance, rate, and time problems, otherwise known as DRT problems. We know that distance is equal to rate times time, and we can take this equation and divide by rate and get distance over rate equals time. Similarly, we could start with that distance equals rate times time and divide by time and get distance divided by time equals rate. This gives us three different equations to use for our DRT problems, depending on what information we have been given and what it is that we are trying to solve for. We start off by making a chart where we have our distance, rate, and time up at the top in each column, and we will have some object that will have a specified distance, a rate, and a time. Part of that will be known, some of it might be unknown, or it might be related to the second object. The second object also will have a distance, rate, and time associated with it. Now, if we're given that the two distances are the same for these two objects, then we can equate the rate times time and come up with an equation here to solve for an unknown. Similarly, if what we happen to know is, if we know that the rates are equal, that the two different objects have the same rate, then we could set up the ratios of distance to time and have a proportion to solve. And likewise, if we happen to know that time 1 and time 2, that both objects use the same amount of time, then we can set up the ratios of a distance to rate and have them equal to solve for an unknown. So let's look at a given problem. So we have the speed of train X is 14 kilometers per hour faster than the speed of train Y. We don't have the specific speed of either one of the trains, but we do have a relationship between the two of them. And so that if we say that the speed of train Y is our rate sub 2, we would then know that the train X, or rate sub 1, is going to equal rate sub 2 plus 14. Now, we have to be given more than just this information, so next piece of information is that train X travels at 400 kilometers in the same time, and that's very important, in the same time, they're letting us know that times are going to be the same, that it takes train Y to travel 330 kilometers. So we've been given two very important pieces of information here. One is that the time are the same, so T sub 1 is equal to T sub 2, and we've been given the distances, that D sub 1 is 400 and D sub 2 equals 300. So, the piece of information that we are to find is the speed of each of the trains. So, remembering that T sub 1 equals T sub 2, we have the ratios of the distance to the rate. And therefore, what we are going to do is set up our chart and plug in the first piece of information, which is the distances. So for train X, we have 400 kilometers, and for train Y, we have 330. For our rates, we have the relationship that the train Y has rate R, and train X has 14 plus R. The times were the same, and we're not going to use the time because we're going to be using that ratio of distance to rate to write the equation. So we have this proportion that we can solve. So we'll go to the next page and we will start solving that proportion. We've got 400 is to 14 plus R as 330 is to R. Since this is a proportion, we can cross multiply, and we get 400R equals 330 times the quantity, 14 plus R. Use our distribution property over addition, and we get 4,620 plus 330R is equal to 400R. We'll subtract 330R to get 70R equals 4,620. Divide by 70, and we get that R equals 66. At this point, we have to remind ourselves, what was R? And so we look back at our chart and we said, oh, R was the rate of train Y. And we know that train X is 66 plus 14, so that is 80. And therefore, we now know the speed of both of the trains, and that is that train X is traveling at 80 kilometers per hour, and train Y is traveling at 66 kilometers per hour.